Let's talk about the earthquake that happened yesterday in Canada/Alaska, a large earthquake, magnitude 7.0, that is happening in an area that has produced a lot of devastation and disaster, guys, and now we're nearing 200 aftershocks in the high magnitudes. This is very scary. We might all remember the Lituya Bay Tsunami, and we might all remember, even if we're not alive, a magnitude 9.3 earthquake. So are these aftershocks that are following this magnitude 7 earthquake that happened yesterday, really at the border between Canada and Alaska, are they normal, or are they a precursor to something bigger? Because there's so many, and there's so many in the higher magnitudes. And this is exactly the question that many people are asking right now. And you, my viewers, have asked me that as well. So here is an update. Welcome, everyone. Thanks for tuning in. Because the thing is, when you open up a live earthquake map of some agency and you see dozens and dozens of new quakes, I'm showing you the images here from the USGS. It's so many quakes, I can't show you all of them, but I'm just showing you a few screenshots. I guess you get the message of that. And all of them are lighting up the same region with all these dots like clusters. Your instinct usually tells you that something is escalating. It looks like the earth is becoming more unstable by the hour if we look at that. But what you're seeing is not an escalation, it is physics, and it follows rules that scientists have measured for more than a century. But that doesn't mean this is critical. Let's start with the beginning. What has actually happened? Yesterday, a magnitude 7 earthquake struck southern Alaska near the Hubbard Glacier. That's why they call this the Hubbard Glacier earthquake. And it's along a fault system. We talked about this in my video that I released yesterday. It's in the end screen if you want more information about that. Along a fault system, the Fairweather Fault, that's the northern end of the famous Queen Charlotte Fault, in one of the most tectonically active regions on Earth, guys. We've got so many volcanoes there. We've got so many earthquakes there. And this area sits basically directly above the boundary where the Pacific plate is being forced beneath the North American plate. And where something like this is happening, never good. So we already do have a powerful subduction environment that is capable to produce both very large earthquakes and also a complex secondary faulting. And that's what we're dealing with here, because the area where the 7.0 earthquake happened is a fault that is comparable to the San Andreas fault. It's like a strike slip fault. And when that magnitude 7 earthquake occurred, a large section, not a small one, a large section of that fault, the Fairweather Fault, suddenly broke, and it has released decades of centuries of stored tectonic stress in just a few seconds. And that energy has raced outward through the crust and has instantly changed the stress balance across a wide region, not only the small, teeny tiny area. And here's the key point that explains everything, guys, that is following now after this earthquakes. So the stress is not released evenly during a large earthquake like this. Some parts of the fault unload violently, and other nearby sections are basically suddenly pushed closer to failure, but don't show failure yet. And the sudden redistribution of stress is what is creating these aftershocks that we're seeing right now. We all remember the magnitude 8.8 Kamchatka megathrust earthquake this summer. We're still seeing the aftershocks in the magnitudes 5. So within minutes after the main shock yesterday, the first aftershocks already began, then more followed, and then more again. And as of this morning's data analysts have worked through approximately, it's nearing 200 aftershocks above magnitude 3. 200 above magnitude 3. If we're going below magnitude 3, even between 0 and 3, we're having way more than that. So that number alone sounds really dramatic. But in the context of the earthquake's physics, it is normal for a magnitude 7 event in this region. But we have seen, when it comes to bigger earthquakes, we've seen this in Japan, a magnitude 7 can be a precursor earthquake. Good thing right now is that the monitoring agencies have not reported any landslides that have been detected so far, because that's always a risk, especially in this area. But scientists have noted something historically significant. This earthquake occurred on the same fault system that has led to the 1958 Lituya Bay Tsunami. And that's why we have to be extremely careful what is going on there. That sentence that I just said understandably raises quite a concern. Let's briefly look at what the Lituya Bay Tsunami actually was. In July 1958, a magnitude 7.8 earthquake struck along this very same fault that we're dealing with right now, the Fairweather Fault near Lituya Bay in southeast Alaska. And the 7.8 earthquake has triggered a massive rock slide. Basically, an entire mountain slide collapsed into the narrow inlet of Lituya Bay. That's the bathtub effect. Approximately 30 million cubic meters of rock crashed into the water almost instantly, guys. They displaced basically water that had nowhere to go. We know all these images when a little bit bigger people jump into a pool. The wave that happens, it's amazing, guys. Water can't go anywhere but up if you have these narrow fjords with the steep walls. So the result was the tallest tsunami that was ever reliably recorded in human history. The waves at that time have reached an astonishing height of about 524 meters. That's over 1,700 feet, guys. That's huge. This tsunami has stripped trees from the mountainside, and basically everything that was left was naked rock. So of course, this was not an ocean-wide tsunami, something that we have seen after the megathrust earthquake in Japan in 2011. It was not generated by subduction megathrusts. It was a localized landslide generated mega wave, so to speak. And thankfully, it was confined almost entirely to the geometry of that narrow single bay. And the key trigger, of course, was not the earthquake alone. It was the combination of the strong earthquake and then the massive unstable slope directly above it, above a confined body of water, came down. So that distinction matters enormously when we're analyzing a present day risk. And that's why I said, thankfully, no landslides have been reported. Let's get back to the present. Although yesterday's earthquake occurred on the same broader fault system, the Fairweather Fault, no comparable landslide, thankfully has been detected so far. And without such a collapse, a Lituya Bay type mega tsunami will not form. But since we have so many aftershocks, if there are unstable areas, through constant shaking, something can always get loose. So if you're in a fjord in that area with your boat, I'd be careful. So now let's have a look what we're seeing on these earthquake maps. So all these aftershocks that are lighting up the region, they're not separate disasters. They're the crust that is adjusting to the sudden change in stress that is caused by the main rupture. And this follows a scientific rule that actually has a name. It's called Omori's Law. That law says that aftershocks occur most frequently immediately after the main shock, and then they gradually decline over time. Right after the main shock, activity was intense, and then hopefully we will have that predictable downward trend. So right now, the dense burst of aftershocks does not necessarily mean that the system is spiraling. It means the system is dissipating energy. Why does this look so especially extreme here in Alaska? Because this is a massive, already fractured collision zone. We have to call it a collision zone. We have the deep subduction interface. We have the shallow crustal faults. We have these strike slip systems like the Fairweather Fault. They call it the San Andreas Fault of the North. These strike slip systems. We have internal fractures within the subducting plane. And of course, these structures are constantly under stress, even when there's quiet times. Alaska records thousands of earthquakes every year. So when we have a magnitude 7 occurring in this area, in such an environment, the stress redistribution affects many faults that are in this area at once. So small faults that were already near their breaking point, they suddenly slip and they contribute to the number of these aftershocks. And every one of these slips appears as a new dot on the map. That's what you see here. So that does not mean the system is destabilizing. It means many tiny locked sections are releasing stress in small increments instead of holding it in like one dangerous block and then poof. So now let's have a quick look at the history of this area, because history provides the clearest answer to whether this means something bigger is coming. Because if we have areas that have these kinds of earthquakes more often, we can learn from that. In 1964, guys, Alaska was struck by a magnitude 9.2 earthquake. Huge. That is the one that we're all afraid of. This was the most powerful in North American history so far. We all know the dangerous Cascadia Fault on the west coast of Canada and the US is getting ready. There's new data that are very concerning. I'll put that video in the end screen for you. I have just released it a few days ago. But 1964, that magnitude 9.2, that rupture was stretching for hundreds of miles, and coastlines rose and sank by many feet, many meters, and then tsunamis crossed the Pacific Ocean. And the number of aftershocks that this earthquake produced will blow you away. It produced thousands and thousands of aftershocks that continued for more than 2 years. That's why we still see so many aftershocks in Kamchatka after this megathrust earthquake. Hundreds of earthquakes, hundreds of these aftershocks were larger than magnitude 4 and several exceeded magnitude 6. And yet, even after this iconic rupture, the Earth did not escalate into something larger. Well, many of you might say, well, that was already the largest thing, right? 7 could still be a precursor for a magnitude 9. We've seen this in Japan and even in Kamchatka. So in the case of that megathrust earthquake, the 9.2, nothing worse happened. That was already the worst. And then it entered into a long and slow relaxation phase. And that event became one of the foundation of modern aftershock science because they learned from that. And let's jump to 2018 right now. Anchorage was struck by a magnitude 7.1 earthquake. Severe damage was happening across the city. And in the year that followed, more than 2,000 aftershocks were recorded. Several exceeded magnitude 5. So if we compare this to what we're seeing right now after yesterday's earthquake, yeah, we can say, yeah, that has happened before. And also after the Anchorage earthquake, many people feared that the shaking meant something larger was building. Thankfully, it never did. But the thing is, it can. So we can't get out our camping chairs and relax and look at the ocean. We could still see something bigger there and a big tsunami. In the case of the Alaska earthquake, the sequence decayed exactly as it was predicted. But then in 2020, the Aleutian Islands experienced a magnitude 7.8 earthquake. Again, Thousands of aftershocks followed. Several were of magnitude 6 or higher, and again, no larger rupture followed. Of course, these examples are critical, and hopefully we can say what we're seeing now and what we're counting near the Hubbard Glacier earthquake, these aftershocks, are not extreme if we compare this to these past events. They're not unusual. It's consistent with Alaska's long seismic history. What makes today's aftershocks feel different is not the physics. It's probably that technology. Modern seismic networks can even detect super tiny earthquakes that would have gone completely unnoticed decades ago. Okay, we're saying we have so many aftershocks above magnitude 3. These are not tiny. But of course, we can detect more earthquakes, and that might look a little bit more overwhelming. But we cannot deny there is a core fear behind all of this. Is this a precursor to something bigger? Statistically, the answer is very clear. For a magnitude 7 earthquake, the probability that a larger earthquake will follow on the same fault system in the short term is low. It's typically around 2 to 5%. That means in roughly 95% of cases, the main shock is the largest event in the sequence. Aftershocks occur in a system that is losing stored elastic energy, not gaining it. They reduce stress, actually. They do not recharge it. Magnitude 5 and 6 aftershocks can still occur. That is still considered normal. So the chance that this system right now suddenly escalates into a larger than main shock rupture is small. The only period where we have generally elevated risk is the first 24 to 72 hours. So we have to wait a little bit longer. That's when the strongest aftershocks most of the time occur. And that's when damaged structures are at the highest risk to finally collapse. That is when secondary hazards are most likely, like landslides. Any day, as days pass and the aftershock rate declines, the probability of larger follow-up events is also dropping even further. And there's another common misunderstanding. That's the idea that aftershocks build towards another major earthquake. In reality, aftershocks are the process by which the fault unbuilds the stress left over from the main rupture. Of course, we need to be able to be sure that these are aftershocks and not foreshocks. That's often the problem. So guys, I hope you like this update. Check out the videos here in the end screen. A lot of interesting stuff is happening above us, below us, and right where we are. Thank you for watching. Please like and hype this video, share it with your friends. And if you want to buy me coffee, link is in the description. Thank you for your supers. Shout out to all my members. Thank you for joining. Click here. I see you in a second. Bye-bye.